All right, you crazy kids, here is your lecture on periodic trends. So, we're talking about specific patterns in the properties of chemicals that are revealed in the periodic table of elements. Neat. What does that really mean? There are 4 things we're going to be talking about. There are trends, and by trends I mean period trends and group trends. Remember that periods are from left to right, and groups are top to bottom. That's just what they're called. And we're going to define them, talk about them. Hopefully they make sense to you. So atomic radius. Atomic radius, by definition, is half the distance between the nuclei of identical atoms that are bonded together. What that means to you is the size of the atom. In reality, what they're talking about is when you have 2 identical atoms that are bonded together. It kind of looks like this. Maybe these are 2 hydrogen atoms, and they take half the distance between the nuclei, and they call that the atomic radius. So like from here to here. Now, why do they do that? Because the edge of the atom is fuzzy. You can't really find the exact edge of it. The electron cloud is an area of probability, not a pinpoint location, but the nucleus itself is a pinpoint location. But you don't really need to know, because what I want you to know is when you hear the words atomic radius, we're talking about the size of the atom. So, period trends and group trends. From period, as we move from left to right, what happens to the size of the atom? Well, as I move from left to right, I'm filling in electron locations, all right? So maybe I have 2s1, and then 2s2, and then 2p1, 2p2, 2p3, 2p4, and so on. Is the atom getting bigger or smaller? At first glance, it might seem like the atom's getting bigger because you have more and more electrons. But remember a couple things here. First, I'm not adding any shells of electrons. This is all in 2. So no additional shells of electrons, but I keep on throwing electrons in there. My number of protons is increasing. That's true. I have more protons. And what's that going to do? So if I have more protons, you would think I'm going to have a greater attraction from these outer shell electrons, which is true. What we also need to remember is something called effective nuclear charge. If I look at 2 specific elements, maybe we'll look at sodium and chlorine, perhaps. All right, sodium, it would be 3s1, and everything below it is filled up. I'll have to show you it. I didn't want to, but I have to. So 1s2, 2s2, 2p6, 3s2, 3s1. Got it. That would be sodium. Its ENC, as we know, should be +1. That's the difference between my inner shell electrons and my outer, and my number of protons. So I have 11, I have 10, +1. I compare that to chlorine. 1s2, 2s2, 2p6, 3s2, 3p5. Oh, now we get an ENC of +7. I have 17 protons, so more protons is true. And I have a greater effective nuclear charge. That greater effective nuclear charge is going to grab these outer shell electrons and pull them in closer to the nucleus. So what happens as you move from left to right on the periodic table? Well, the atoms get smaller. If I were to grade a question like this, and you simply told me the atom gets smaller, that would be probably 1 point. If you told me the atom gets smaller because your effective nuclear charge is increasing, along with the number of protons is increasing, creating a stronger pull on your outer shell electrons, drawing them in closer to the atom, that would be worth 2 points. So maybe a 3-point question. If you simply give me the answer of smaller, it's worth 1. But if you tell me why it gets smaller, that'd be 2 out of the 3 points required. So that is your period trend. So moving from left to right, it gets smaller. Why does it get smaller again? If your effective nuclear charge is increasing, you're not gaining any shells of electrons, you're getting more protons, and because you have an effective nuclear charge that's increasing, it's going to pull in those outer shell electrons with greater force, drawing them closer to the nucleus, resulting in a smaller atomic size. Wow, that was fun. Let's do group trends. I'm going to erase this stuff and take a look at our group trends. So our group trends, if I just go down the alkali metals, maybe we'll go 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. You should see now that I have these shells that are stacking on top of each other. If we remember, we had 1s, 2s, 3s, 4s, 5s. So moving down the periodic table from top to bottom, all these shells stack on top of each other. The result is the atom gets bigger. And then why does it get bigger? Well, I have shells stacking on top of each other. So you might pull out an example, compare sodium to potassium. Sodium has 3s, potassium has 4s. 4s stacks on top of 3s. Therefore, sodium in comparison to potassium has to be smaller because potassium has that 4s location being occupied of the atom with electrons. All right, so that's the reason why shells stack on top of each other, atom gets bigger and bigger and bigger. Cool. You might make the argument that I also have more protons. So why doesn't the atom get smaller? It got smaller up here because I had more protons, but remember, these are all in the same shell. Now I have these additional shells that are stacking on top of each other, and this group trend outweighs the more proton trend for your period trend. So if I were going in a diagonal, which one's going to have a greater influence, the addition of shells or your effective nuclear charge, the additional shells has a greater influence on the size of the atom. All right, now ionic radius. You guys should probably remember we have cations, we have anions. Cations are positive, they lose electrons. Anions are negative, they gain electrons. At first glance, it should make sense. When you lose something, you should get smaller. When you gain something, you should get bigger. But why? Why does this happen? All right, let's take a look at an example of a cation. Maybe sodium again. 1s2, 2s2, 2p6, 3s1. Ooh, that kind of looks like something weird. I'll go with 1. I legit think a giant limb just fell on my house, but I will investigate later. This seems more important. Now I'm totally a chemistry teacher. All right, anyway, so what electron is going to be lost here when sodium becomes a cation? All right, it's a metal, it's on the left side of the periodic table, it loses that electron. Here is the electron it loses. So the 3s location is vacated. I no longer have a 3s electron. That shell is now empty, and my resulting size is a lot smaller. So why does it get smaller? You're losing shells of electrons. Your valence electrons are the ones that are lost when you become an ion. You lose that valence electron, the outermost shell is gone. It's vacated, no longer occupied. Also, I'll now have more positives and negatives. So I had 11 positives, 11 negatives. Now I only have 10 negatives to my 11 positives. After it loses that shell, the resulting pull on these electrons is going to increase because you have less negative things out there. But the most important thing is the loss of that shell. That's what you should be mentioning. All right, anions. Why do they get bigger? Let's take a look at an anion. Maybe chlorine. Wow, I probably should have just left that electron configuration. I could have copied it over. Oh well. 1s2, 2s2, 2p6, 3s2, 3p5. All right. So fluorine's got, 9. Oh, wait, I did chlorine. Oh, good. Chlorine, we'll do chlorine. Chlorine's going to have a -1 charge. It's going to gain 1 electron in this location. So I'll have 1s2, 2s2, 2p6, 3s2, and 3p6. I'm adding an electron, but I'm not adding any protons. So I have 17 positive things, but now I've thrown in yet another negative thing. You should remember that negative things repel. I'm throwing an electron into an existing shell, so it's not getting really any bigger. I'm just adding an electron in there. And because electrons repel, they're going to repel from all the electrons in that shell, and they're going to spread out. So my resulting size is going to increase or get bigger. Cool. Group trends follow the same trends as atomic radius. You get bigger. Why? More shells. Period trends, however, are kind of weird because, oh, that was a tough periodic table move there. You have to remember on the periodic table, as you move from left to right, you're transitioning from metals to nonmetals. That means you're transitioning from cations to anions. So there's no real period trend. No. But I might ask you about cations and anions specifically. All right. Our next trend is called ionization energy. What is it? The amount of energy needed to remove an electron from an atom. This should pop up a memory of the photoelectric effect. So the photoelectric effect, if you recall, if I used purple light, I could kick out an electron because purple light had enough energy to remove that electron. Red light did not. So it's a very similar stance in that. We have a couple of other words in here we need to define. Well, ion, we're pretty good with that one. Atom with a positive charge. If we're removing electrons, we should only be dealing with positive ions or cations. Ionization is any process that results in the formation of an ion. So ionization energy, we're talking about specifically the energy needed to remove an electron from an atom. What electrons are we removing? We're removing valence electrons. Those are the ones that can be lost, shared, or gained. They're your outer shell electrons. Those are the ones we're going to be removing. A way to think about this would be if I had an atom and I zapped it with energy, the atom's going to turn into a cation, and I'm going to be left with an electron. So that's a little chemical formula for how this thing actually looks. Cool. Let's do group trends and period trends. So as I go down a group, what's going to happen to the amount of energy required to remove an electron? Well, let's look what happens when I go down a group. So 1s, 2s, 3s, 4s, 5s, 6s, 7s, whoops, 6s, 7s. Looks like the atom is getting bigger and bigger and bigger and bigger and bigger and bigger. Because the atom is getting bigger, the protons are getting further and further away from your electrons. And we're talking about the outer shell electrons, your valence electrons. So if you think about it, if the distance is increasing between your positives and negatives, right? This might be 1s, and here's the electron. And this might be 7s, and here's the electron. Due to Coulombic attraction, or the positives and negatives and how they attract, the further away they are, the less attraction you're going to have. Less attraction results in less energy needed to remove an electron. Wow, I really scrambled that remove word. Okay, so the bigger the atom, the less energy that's required to remove electrons because the positive and negatives are simply not as close. Coulombic attraction states the closer things are, the greater force of attraction you're going to have between positives and negatives, and the further away they are, the less attraction you're going to have. So the less attraction, the less energy that's required to remove electrons. So group trend, as you go down, the amount of energy should decrease. Hopefully they've explained that pretty well for you. Period trend. As I move from left to right, what's going to happen to the amount of energy that's required to remove an electron? Well, something about ENC is going to come into play here. Let's take a look at two atoms. So maybe I look at sodium, 1s2, 2s2, 2p6, 3s1, and I look at chlorine again. 1s2, 2s2, 2p6, 3s2, 3p5. ENC on sodium is going to be a positive 1. And I'm talking about this electron right there is the one that's going to be removed. And ENC on chlorine is going to be a positive 7. And this is the electron I'm going to remove out here. Because ENC is so much higher for chlorine, or the effective nuclear charge on chlorine, it's going to be holding on to that electron with a lot more force. Also, the size of the atom is decreasing. If you remember, sodium compared to chlorine, as we move from left to right, the atom gets smaller. So I have a couple things in play here. The atom's getting smaller, making the electrons closer to the protons. So due to Coulombic attraction, it's going to require more energy to remove that electron. But another fact is the effective nuclear charge of the atom is increasing. It's becoming more positive. The more positive it is, also it's going to have a greater pull on that valence electron. Both of those things turn into the fact that as you move from left to right, the amount of energy required increases. Cool. One last thing here, electronegativity. So electronegativity, by definition, is the measure of the ability of an atom in a chemical compound to attract electrons. Believe it or not, there's some attractive elements out there for electrons, and there's some not that attractive elements for electrons. The very attractive elements are going to be in the upper right-hand corner, besides the noble gases, and the non-attractive elements are going to be in the lower left-hand corner, besides the noble gases. You should be able to look at this information in your packet. This is Table A. look at it. You'll notice a whole bunch of values from 0 to 4. Linus Pauling, this crazy scientist, came up with this scale of 0 to 4 to measure the attractiveness of elements to electrons. The more attractive they are, he called that the more electronegative they are. So fluorine is the king of attraction. It's the most beautiful element in the world if you are an electron. Electrons are very, very attracted to fluorine. Oxygen is the queen. All right, if we look on our table, fluorine has a value of 4.0, oxygen has a value of 3.5. Everything else is lower than that. The noble gases are zeros. They are not attracted to electrons at all. Why? Because they're not reactive. Okay, so if you're not reactive, you're not going to be attracted to electrons. If you're very reactive, you're very much going to be attracted to electrons. And you're going to say, oh, why is fluorine the most attractive and not francium? Because fluorine is very small, and those electrons are going to be very close to that nucleus. Very strong attraction. It's going to be pulling those electrons in. All right, whereas francium, very, very big, it's the largest element on the periodic table, not a lot of attraction going on there. All right, so we have gone through our 4 different periodic trends. I would like you to know a couple things about these things. Well, this one you can look up, right? You legit just need to memorize the definition and then use your packet, and you should be all set. But for the other ones, I need to know the period trend, moving from left to right. I need the group trend, moving from top to bottom, and I need to know the reason behind those trends. Why is that trend a thing? If you don't know by now, you can Google it, or you can ask me in class. All right, see you later.